Hello, and welcome to Team 58's Project 2 presentation on the analysis of air quality improvement strategies. In a world of constant manufacturing and never-ending pollution emissions, the worldwide air quality is quickly in the decline, threatening humanity and the planet we live on. Every year, 6.5 million people die due to illness brought on by poor air quality, and around 92% of the global population experiences air quality that can cause serious health risks. Toxic gases such as sulfur and nitrogen dioxide are becoming dangerously potent in most urbanized areas, with concentrations of PM2.5 and PM10 being well beyond the safe threshold for human health determined by the CDC. Hong Kong is no exception here. With a population of over 7.5 million people and highly active manufacturing and power production industries, air quality remains a legitimate and concerning problem, even despite some advances made in recent years. Residents face dangerously high concentrations of air pollutants every day, hurting their health and the overall image of Hong Kong. Thus, the city is in desperate need of an energy and cost-efficient air purification device to be utilized across the city, effectively providing safe, breathable air for all its residents without forcing major changes to its power production facilities. One proposal being experimented with is a design from Dutch artist Dan Roosegaard and his team of engineers. It is a 7-meter tall, smog-free tower, which essentially acts as a large air ionizer, using electrical energy to pull charged pollutant particles out of the air flowing through it to be collected and disposed of later. Though the design shows promise, there is still a concern about whether or not it would be an effective measure of cleaning air on a city-wide scale, both in the sense of cost-effectiveness and sustainability, as the chosen system should be able to run for years to come. To finalize a decision, the city has requested help from an outside consulting firm.
Based on our research, we found that Hong Kong's smog is mainly caused by motor vehicles, industry, and power plants, each compounding the effects on each other's pollutants. The street-level smog, specifically, is exacerbated by diesel vehicles like trucks and buses. 60% of all smog and haze particles and 20% of dust particles are charged therein. This project focuses on removing PM2.5 and PM10 particles, so these concentrations are the main quantities of interest. Next, the height of the purified airspace is related to the magnitude of voltage we apply to the ESP's plate, and the purification efficiency depends on the proportion of charged particles. However, increasing the charge will increase the ESP's energy consumption, creating a higher cost. In terms of T58's model, we researched the myriad factors that affect the ESP's efficiency. Based on this research, we concluded that van der Waals forces and Brownian diffusion forces are relevant because they are intermolecular forces and do not impact the rate at which particles are taken out of the air, so they are not relevant to the model. Finally, air pollution contributes to GDP loss in affected countries, giving Hong Kong an incentive to implement this solution.
The model was created in order to compare the theoretical energy needed to get rid of all the particles within the tower and compare it to the actual amount of energy needed to filter all the particles outside of the tower. So the program needed to consider the forces and calculate the total amount of work needed to filter out all the particles. So various constants were calculated, such as the diameter of each particle, the concentration, and what was made was a mathematical model employing discrete layers from the top of the plate to the top of the tower, along with the area below the plate, and it was used to where the above the plate experiences a downward electric field from the plate, while the area below experiences an upward electric force from the plate. So constants such as the width of the tower and the mass of each particle were calculated, and a Python program makes use of various functions such as calculating the various forces. 4 main forces were found to significantly impact the particles. So these were gravity and the electric force due to other particles within the cloud, the buoyant force, of that each particle experiences in air, along with the drag force. And it was used, each force was summed up according to their correct directions for every single particle on each layer. So each particle's force experience was multiplied by the height of that particle in order to find the amount of work. And the result was multiplied by 2 in order to account for above and below the plate, since the model needed to first calculate one side of the plate and then find the other side. And it did this independently for both the PM 2.5 and the PM 10 particles. And at the end of the program, the energy efficiency is calculated. The power is found by the total work done divided by constant, showing how much is filtered within a single second. And this is compared to the actual power to find out the efficiency, and the number of grams that it's filtered in an hour is also calculated from these results.
After using the model to test different towers, it was decided that as Rosgaard's model was one of the best options available, it would be more cost-effective to use his design rather than spend time and money designing a whole new system and creating new infrastructure to manufacture it. The model calculated that this tower is 30% energy efficient, meaning 30% of energy that is input into the ESP is used toward capturing a given particle. It is found that 144,000 cubic meters of air flow through the tower per hour, but based on our efficiency, about 43,000 cubic meters of air are filtered in reality per hour, reasonably more than Rosgaard's claimed 30,000 cubic meters. This contributes to a mass of about 5 grams of PM 2.5 and PM 10 particles collected by the tower every hour. Given these findings, and the processes needed to run a tower to meet these requirements, each ESP warrants an annualized cost of $2.6 million per tower. Determining the number of towers needed for a city of Hong Kong poses challenges, though, as the numbers needed to clean enough air for the whole city to breathe, and the number of towers needed to make a blanket of clean air across the whole city were vastly different. Using the population of Hong Kong and the average volume of air a person breathes every day, it was determined that only 80 towers would be needed to provide all 7.5 million residents with breathable air. This is a feasible number, as it would be relatively cheap to run, not require much energy compared to the rest of the city, and would take up little space. However, upon examining various human factors, this solution becomes very infeasible. The first issue, as mentioned before, arises with the number of towers needed to clean air for the whole city, based on area. Each tower really only has an 11-meter radius in which the air is effectively clean, before it starts to mix with the ambient polluted air again. To fully blanket the city in clean air, the towers would need to be much more closely packed together than the calculated 80 towers would be, driving costs up and taking much longer to implement and requiring more real estate. The second issue arises when looking at Hong Kong's population density. Like most cities, it is not evenly spread out, with some areas being much more dense, and thus requiring more clean, breathable air. These areas tend to have less available property space, which would pose a direct challenge with the higher number of towers needed. Building high concentrations of towers in one area, or even much larger towers, could be unpleasing to city residents and take up too much space from other necessary infrastructure. Thirdly, various inefficiencies due to weather, power, infrastructure, and other civil determinants can decrease the efficiency of the ESP towers, further changing the differing densities of towers needed across the city. Lastly, the amount of pollutants pulled from the air would be somewhat offset by the extra power required by the city's power plants to run the towers, yielding less efficiency overall. Overall, it would be a hard project to sell, with high costs, space, and power requirements.
While the current plan may be infeasible, there are certainly some ideas that could be investigated further to offer more efficiency and less political headache. Towers could be constructed on top of existing buildings to save space, and recycled materials could be used to save costs. New buildings could leave gaps between certain floors, designated for large-scale versions of the air cleansing system to be implemented without taking up extra ground space. Towers could also be placed in areas where more smog is generated, and advancements in the power production process could be made to yield less pollutants, allowing less pollution into the air as a whole. This has been Team 58. Thank you for listening.